This problem is asking us to figure out how far a projectile, which has a mass of 10 kilograms, will go if it is fired vertically upward. We're given that it has an initial velocity of 50 meters per second, and we want to do this problem twice. The first time we want to neglect air resistance, and the second time we want to use this function right here for what air resistance is, and this function is 0.01 v squared. So let's tackle part A first. So in part A, we want to draw a free body diagram. So if we draw a free body diagram of this cannonball, we have its mass times gravity, which is acting down, and its mass is 10 kilograms. Gravity is 9.81 kilograms. So what's acting down is 98.1 newtons. And I misspoke, gravity is not kilograms, gravity is meters per second squared. So we have a force of 98.1 newtons pointing downward, and there's no other forces acting on this. So this is going to equal our kinetic diagram. And with our kinetic diagram, we have to account for its mass, and its mass is 10 kilograms, and an acceleration, and we're going to say it accelerates in the positive direction. So right here, we're going to define up as our positive direction. Now, if we sum our forces in the y direction, so the sum of the forces in the y direction is equal to a mass times an acceleration in the y direction, this force in the y direction is minus 98.1 is equal to 10 times the acceleration of y. So we get our acceleration of y is equal to minus 9.81 meters per second squared. And this makes sense, right? This number should look familiar because this number is actually gravity. And what this is saying is that while this cannonball is fired, its acceleration, the only acceleration that it sees, is due to gravity. And that's true because this gravity is going to make the ball get to a maximum height and stop and fall back down to the ground. So what is this maximum height? Well, if we use our kinematic equations, because gravity is a constant acceleration, we can figure out what this height is. And since we are not given anything about time, we can use the v squared, our final velocity squared, is equal to an initial velocity squared plus 2 times an acceleration times some change in x. And for us, this is actually going to be the height we are looking for. This height right here. So our final velocity squared is going to be 0 because at the top, when the cannonball cannot go any farther up, it has a velocity of 0. And it's equal to its initial velocity, which is 50 meters squared, plus 2 times this minus 9.81, which is gravity. And it's a minus because of how we've defined our positive convention, is equal to h. And when we solve for h, we get h is equal to 127.4 meters. And it's a respectable number. So this is saying that when this cannonball is fired with an initial velocity of 50 meters per second, it gets to a height of 127.4 meters above the ground. Okay, let's look at part B. And for part B, we need to draw our free body diagram again. And the same force, this 98.1 Newton, is acting down, and which is still due to the weight times gravity. And we also have another force which is acting down, which is this force of air resistance. And we've been given that the function for air resistance that we're going to use is 0.01 v squared. And this is equal to our kinetic diagram, which is going to have a mass 10 times an acceleration ay, and we're going to assume it's a positive acceleration. And then we are going to sum our forces in the y direction again. So when we sum our forces in the y direction, sum of the forces in the y direction is equal to a mass times an acceleration in the y direction, we have a minus 98.1 minus 0.01 v squared is equal to a mass, which is 10, times an acceleration in the y direction. And if we solve for our acceleration in the y direction is equal to negative 9.81 minus 0.001 v squared. And this is a more interesting equation than we had right here. This is saying that the acceleration is a function of velocity. And since acceleration is a function of velocity, we can't use these kinematic equations. We can't use the same equation that we used for the first part. So we have to go through and look at our alternate equations for acceleration. So one of these other forms of acceleration is equal to a velocity times the derivative of velocity with respect to displacement. And we are going to use this equation right here. We're going to separate our variables and we're going to integrate, and we're going to figure out what this height is for this cannonball. And if we first substitute in our expression for velocity, for acceleration right here, we have a minus 9.81 minus 0.001 v squared is equal to v dv over dx. Now we want to separate our variables, and when we separate, this is going to go to the other side because it has a velocity in it, and our x is going to come up here. So we get dx is equal to v dv divided by minus 9.81 minus 0.001 v squared. And now we have to just figure out what our bounds are. Well, we're looking for how high this goes, so let's call this x final, let's call this h. And our x initial, well, we're going to call this 0 because it starts at a 0 point. And for our velocity, we know when it gets to the top point, like we said before, our final velocity is going to be 0. And we were given an initial velocity of 50 meters per second, so that's what we'll put in our lower bound. When we perform this integration, we get x evaluated from h to 0 is equal to minus 500 times the natural log of v squared plus 9,810, evaluated from 0 to 50. And if we plug in these bounds, we have h is equal to 114 meters. And this is the height that the cannonball gets when we account for air resistance with this expression, this function right here. And this makes sense. If you think about it, the expression we had without accounting for air resistance was this 127.4 meters, and our expression with air resistance is only 114 meters. So that means when we neglect air resistance, it's going to go higher than when we account for air resistance, and that makes sense.